encourage you to ask questions. I know that backgrounds are sometimes difficult and different, so I really encourage you to stop me anytime and ask for clarification. I will try to do my best, but this is always difficult. So today I will focus on decay time estimates. Right, I should probably add here the word time. And that gives me also a good test whether my pen is in the right position. So I have to correct that too. Sorry guys, but if I want to use this, this always changes its format. Okay, so I originally planned to talk about decoherence times, but I have the feeling for me, decoherence always has a slightly different mathematical meaning. So I was a little bit careful about using that word. I know that it has a lot of meanings for, in applications, very meaningful. And I will just let you decide how far this has to do with decoherence time or not. This might, in some cases, be relevant or not. This is joint work with my students. I definitely want to emphasize Haojian Li. She has a really major part in this current work, but I'm doing this for something like 2 years with different groups of students and collaborators. And so it has been kind of fun to find out. And the fun part is that I want to estimate, how long does it take until something reaches an equilibrium. And this is not only a physical, but also mathematically extremely challenging program. So this is the fun part, to see that motivated by quantum information theory, we have really deep mathematical questions to study, and that's what we do. So let me start with a very obvious sentence. Quantum devices are potentially amazing. I think, you were not here if you wouldn't potentially agree to that sentence. But we have to be careful in how we interpret this sentence. There are different tasks which we look for. There could be new quantum tasks, right? Teleportation is a wonderful motivation. If you want to motivate students to do quantum, teleportation is a good thing. Bell test, we have seen it. Of course, if you want to really go into computer science and show that something does better, like Shor algorithm or low depth circuits. So there you want to actually beat the classical word with a quantum device and make use of quantum advantages. And then of course there are things which are sort of in between, and I would, the supremacy test might be looking for the tasks which are more quantum motivated, and then they will be formed better. But of course, supremacy should be somewhere in between the two, right? But there are some tasks, for instance, if you want to understand the configuration of some molecules, where maybe a quantum computer could be better because it just understands large numbers of particles better than a classical computer. That's kind of the big picture, or is less, very lax formulation. But we should distinguish these different kind of aspects of quantum information theory. And I probably, my work is probably more about somehow showing that certain things do not happen as fast as they should, or that, often we lose a lot of entanglement in a short amount of time, and we want to know how much and how fast. So I just want to stress these different aspects. And this is the one I'm really fascinated about. It's not directly related to my research at first, but this is the famous, it's a Gedanken experiment by Hawkins, but I think Prescott and Payton have put it into formalism. So here it is. So this is supposed to be a black hole, right? And they are throwing, so let me start from the beginning. So Alice has an entangled state here, and Bob has an entangled state. And part of the state they put on a rocket. Alice puts A prime on a rocket and Bob puts B prime on a rocket, and they send it into the black hole. And I have to admit, I stole this picture from the internet, but it's a nice picture, and who knows how a black hole looks like anyway. Then the black hole, emits some gamma radiation. This is the D part, the gamma radiation part. And Bob is a very super powerful Bob. So this is why he gets this double bar. He not only can put part of his state on a rocket and send it to the black hole, but he also has observed the black hole forever, or for a long time. and remembers the, so he remembers a lot of the original state of the black hole. And you have to understand that you're dividing this Hilbert space, which is in the background, the one from A prime and B prime. So this is the part, A prime is the part which Alice puts her secret in, B prime is the rest. So if Alice has a small secret, Bob has observed the rest of the black hole before. That's usually a large state, right? So I mean, this is why I say don't try this at home. It's not very realistic, but I mean, it's still a cool experiment, because what happens is, although a black hole doesn't really send anything out by the gamma radiation, if you then measure the gamma radiation and you remember, Bob remembers what happened before in this entangled version, then he can actually get Alice's secrets by just looking at the gamma radiation and what he's done before, right? By the way, he cannot detect the secret by just looking at the gamma radiation, and he cannot detect the secret just by looking at what he had before, because these things here are spatially separated. So just by looking at Bob's parts alone, he has no idea what Alice had put in. Just by looking at the gamma radiation, that's the same thing. And so the starting state, thank you for asking, Paul. The starting state here is, we really start with the tensor product PAA prime, tensor CBB prime. So the state which was written at the beginning, that is the initial state. And sort of, you have to understand that, this is a very good point to explain that. So here is this unitary which models the black hole. That is a quantum mechanical assumption, and we keep, the A part. So this will be here an A, C, D, B part, right? This is the whole state which we obtain, where we have to understand that this part here and this part here do not undergo the unitary evolution, right? So these parts are, I mean, we should really imagine that there's space outside the black hole where we can send the message completely undisturbed through. And this is happening on these two parts. And the CD split here is really, our Hilbert space is A prime tensor B prime, and that is the same thing as CD. So C goes into the black hole, so we don't have access to this. And D is the gamma radiation. But the initial state is the tensor product of these two states prepared by Alice and Bob separately. Does that answer the question? Good. But this is really important, because for what we do later, it's important that we not only control what happened with the unitary, but we have these entangled pieces which we have to control as well. So thanks for asking that question. It gives me exactly the thing which I have to explain for the future, right? So and let me just talk about what, so here I rewrote, so these slides I can make available. I just wrote in words what I just said. And Bob has this double B because he's not only the B or B prime component, because he really has to look at these parts together, D and B. So he has to observe what happens before, and he has to prepare the state in advance. So this is why this is a very powerful, it's a very large requirement if you want to do this physically. I don't know. Anyway, so I have some mathematical quantities which we use to measure the statements which I'm talking about. So I will get them out of the way. I hope some of you have seen the von Neumann entropy for states. So rho here is positive semi-definite and has trace 1. And yeah, I know that some of you have seen my right. So I've written many traces in my life, and they become a little bit deformed, right? So we have a positive definite. So remember that usually we have a state, but if we mix states up, this becomes a density. So mixed state. So rho here is a mixed state, and for this we need the von Neumann entropy. We need the relative entropy, which is given by trace rho ln rho minus trace rho ln sigma. So the relative entropy is, I will step back. You want to step me back immediately, James? Okay, do you have a question? I can't hear you, so you have to say something.
Okay, I just was looking at that last point. Bob observes the gamma radiation D emitted from the black hole. Up to some small error, Bob can reconstruct the density matrix of Alice's A and A prime from D and B. That's the whole point, right?
That's the whole point.
Okay, good.
And
Thank you.
if
I didn't read that fast enough before you went to the next slide.
That's perfectly okay. And this actually is also the motivation for the next slide, because reconstruct is some qualitative statement. And so I have to tell you, in which sense can he reconstruct? And that's where the math kicks in, because you have to give some criteria, right? So that's why, yeah. Yes, the black hole, that's exactly right. So I think the idea is that the black hole is super mixing. So Paul asked whether this comes from entanglement swapping. Of course, I think the black hole is because we don't really know what happens inside. They assume that this mixes around everything. Everything which goes in is swapped around in a most destructive way. And then the gamma radiation is some random piece which is put out of the black hole, and we don't know what it is. So in this whole point is that we don't know what D is. In many things, we only know the size of D. So we know how much gamma radiation came out. But in terms of which information came in and which information came out, the relation is supposed to be almost random, right? So this is the entanglement swapping you mentioned. That's exactly right. Good, so I will go back to my math expressions. So we have the relative entropy. I want to mention that this term here is often called cross entropy, and that was used in the Google experiment. And in terms of mathematical size, it's kind of a little bit silly. I mean, cross entropy is motivated from information theory, but relative entropy is relatively stable and has a lot of good properties, which is not the case for cross entropy. And you're just adding a fixed number here if rho is fixed and sigma varies. So mathematically, this relative entropy is more stable, but I mean, you use what you can and have to use in order for benchmarking, right? So cross entropy and relative entropy are tightly connected. So is mutual information of relative entropy. So mutual information is always an information between two parties. You have a state in two parties, A and B, and you measure the entropy of A plus the entropy of B minus the entropy of AB. And that is exactly the relative entropy of rho AB, rho A, or AB. So if you have not seen this, let me just write this down. So, you have usually a density, rho AB. That is the density on a joint Hilbert space H is A tensor B. And rho A is just Alice's part, and that is identity tensor trace B of rho AB. So this is a convention in quantum information theory that we understand for a joint density, the marginals as one obtained by partially tracing out the A and B part, right? So this is whenever you have a joint density, right? So this is the important point, right? So mutual information is something which measures a joint, quality of a joint entropy of a joint distribution. And this I3 entropy, which is really a little bit mysterious if you see it for the first time. So if you find this kind of troublesome, well, be my guest. I felt exactly the same way. But it's a funny thing. It's mutual information from AB to AD minus the mutual information from A to BB, right? So A with B, A with D minus A of BB. This has a lot of symmetry properties, and that's why they call it I3. But let me just say that the rule is that if I3 is very negative as it could be, then they call that phenomena scrambling. So this is how we want to measure whether Bob has a successful strategy to recover Alice's secret. this is not unproblematic. I mean, you could say, well, this is maybe not the best way to measure that. And this would be, time for another talk. So, we will accept this for today. But it is certainly, it's simply what is done in the literature at this moment. It has a good reasons, and it's also funny that the best situation is where this I3 is very negative. And so, okay, but I think at this moment we just have to accept that because that's what has been used in the literature, and it's also fascinating. So this I3 is a little bit mysterious, but it is important. I want to mention that this is related to out of order correlation. So the other thing what you sometimes measure is you have a certain density, you apply a unitary, and you measure this term. Or you could, so this is a correlation with respect to u. You could also replace this here by a sigma, and this term, this is why I asked Paul, is related to when you measure non-classical lights. This is very close to this correlation term, which is actually sometimes measured. And we could do a similar, we could similarly call correlations. And if you prove that you have I3 scrambling, and many times you also know something about these correlation matrices, right? These for different rho and sigma, we actually know quite a bit, but that's not the main purpose of the talk. So the main purpose of the talk is the following: taking a Haar unitary. So you have a large Hilbert space, and you take a random unitary. This is really hard to simulate in any given experiment. I think probably everybody agrees on that. So we want to replace this unitary by something easier. Now, it cannot be easy because the scrambling somehow expresses maximal entanglement swapping, so it cannot be that simple, right? I mean, it has to do something destructive. So here's my proposal. We fix 2m many unitaries in a given Hilbert space. We assume that we also have the inverses. So from n plus 1 to 2m, we list the inverses. We make sure that the inverses are there, and we give weights from 1 to n. Then we take a large T and Poisson processes, which jump, according to these weights, right? And for a given number T, we list all the jumping times for all these m different Poisson processes. And whenever we see a jumping time, we write down a unitary which corresponds to, these are labeled Poisson processes. We know which group element corresponds to which process. So we label all the times, and then we write down all these unitaries, which we have taken from our given list. And that unitary is supposed to be scrambling. So this is a random gate in many ways. Many things can be said. I mean, a random gate is just a collection of random unitaries, and these unitaries a priori are arbitrary. So you can choose the one you can actually work with, in principle, right? So if you have certain things, for instance, unitaries which you consider local, right? I mean, if this are given local unitaries, you take a certain iteration of these local unitaries, and we want to show that these things do scramble if you take enough of them. If you talk about the depths of the gate, that would be the total number. Well, I mean, the total number of gates is, of course, capital N. And if you have Poisson processes, you know what that is because you have m of them, and you take the expectation over pt wj, and that's t times wj. So if you know the time, you know how many unitaries you need. And if they are local, you can maybe arrange this to have smaller depths, but depth is a matter of what is local and how many of these UJs overlap. So that's something which is which has to be discussed on a case-by-case basis, because in itself it's not well defined under these assumptions. And this is not the first time we do this, but something similar has been observed for Brownian motion. And it's also known that this has to do with 2 or 4 designs depending on your definition, that this actually leads to scrambling. So this is known. However, I think the I3 estimate, so the mutual information estimate, were not done as rigorously as I could think. I mean, people write articles assuming that, if something is generic, it does happen. But that's not often a concrete estimate which we are interested in. But the key question here is, it's about time. No, it's, how long do we actually have to wait until that happens, right? So this is my, my time horizon, which I want to understand. And I want to find some estimates. And we conjecture that if the unitaries are reasonably chosen, this should always happen. So you can always have an estimate for the time. We can verify that in some examples. And we have developed the theory to do so, but that's part of the work I'm working on. Good. So far, is the goal clear? Okay, good. So yes, here's a blank page. So these unitaries are pretty arbitrary. So let me give you some which are kind of concreter examples. You start with a Hilbert space and you take d copies of it, right? So this could be just d qubits, right? That would be a good example. And then you're given unitaries u, j, l acting on S1 up to SD. So these are labels. Here's SJ and SL. They are what you think they should be. You just flip-flop around these two coordinates, right? So these are flip maps, right? They flip some positions. And that is a good, that is a good example. And then there are two cases. You can only allow uj, j+1, so neighboring flips. That would correspond to locality as I understand it. Or you can allow all flips, right? I mean, between arbitrary parts of your tensor, you could flip any two positions, right? And the times we expect to see are drastically different, right? So in this case, we probably expect a time which is of the order log. I mean, it's essentially d over something large. I think people actually expect this to be d to the 2 to the d. And here we expect d to be of the order. So the waiting time, something like d squared. No, d squared times 2 to the d. So yeah, that's my guess. But we are still working on the concrete estimates, but we know that this sort of works. What you see here is that you have a trade-off, right? I mean, if you want to perform this amazing task of doing scrambling, which is known to be an amazing task, then if you want to be too local, then you have to use many unitaries. And if you allow non-local interactions between different positions, then your time is much faster. So there's always a trade-off. You cannot say this one is better or that one is better. It really depends on what you can realize and what how long time you have to wait and how big your lab is at the end of the day. So this is the point. I mean, it's really, one has to make a balance here and one has to find a good way to understand this. Good. So my trick for all of this is to follow, this is math, right? So we follow things which we know. And we do know something about classical heat semigroups. So let me tell you a little bit about classical heat semigroups. I think some of you must have seen this Laplacian on RD, right? So d squared by dxj squared, and that describes the heat semigroup, and that solves this PDE. This is actually ODE, ordinary differential equation. And if you have a certain initial function, an initial eigendistribution of the heat, then you just wait a little, and then that's how we get the heat distribution. I think this should be pretty standard. Then people have copied the same idea and call it Laplace-Beltrami operator on a manifold. If you don't know what a manifold is, just a surface or something in high space, and then since it's a surface, you don't have all directions available. You can only travel in the directions given by your tangent space. And then there's something called Sub-Laplacian, and I had no idea about Sub-Laplacians like 3 years ago. I didn't care about them at all, but they turn out to be important. So this is how sometimes it happens. So So the difference between Laplacian and the Sub-Laplacian, I will show a picture in a moment, is essentially the following. You have a manifold, and a manifold has a certain dimension, right? I mean, it's a surface embedded in free space, so the dimension is 2. So if this has a certain dimension, the tangent space also has a certain dimension. So the Laplace-Beltrami operator takes a basis, locally a basis in every possible direction. So if the surface is 2, you have 2 of these guys. If it's a 3-dimensional object in 4 space, it's 3. And the Sub-Laplacian does take not all directions, but some of them. And that's it, right? So let me give you an example which is pretty relevant. This is the 3-sphere in R4, right? So it's a 3-dimensional manifold, has XYZ coordinates, which are called XYZ and resemble our, X, that they resemble this matrices here. Is actually not a coincidence, because S3 is also somehow locally isomorphic to SU2, the unitary group in 2 dimensions. So these XYZs are really your favorite Pauli matrices, which I hope you have been able to appreciate so far. And of course, you know that if you take the commutator between X and Y, that this is not X, which I mistakenly wrote, but it's Z. So if you take the commutator of 2, you get the third one. So Sub-Laplacian is exactly this. If the 2 generate the missing 1, then you can only work with fewer vector fields. You only work with x squared and y squared, whereas the full Laplace-Beltrami takes x squared, y squared, and z squared. Yeah, so this means we are differentiating in the x direction, we're differentiating in the y direction, and we are differentiating in the z direction, and this gives us a second-order differential operator, or we only do it in 2 directions, and we want to understand these 2 geometric objects. And whenever you write down a differential operator, then you can look for the heat semigroup generated by that operator, and that's what we use here. And then once we have such so what we get at the end of the day is the semigroup, right? So the semigroup here is always right. So and this has a property that TT plus TT times TS is TT plus S. That's the semigroup property. And then we want to measure how long does it take until the semigroup has almost brought everything back to the equilibrium state. That's the question we want to answer, time to equilibrium. And there are different ways to measure that. We will always assume, the semigroup property I explained. We will assume that we have a continuous action, which in many cases, probably some people here prefer unitary. We will come up to this later. We will assume it's ergodic, so the only invariant state is the identity. It's a mixed state, and our notation is the 1 norm for the corresponding, given by the corresponding measure. And then we have different concepts of time to equilibrium. This is qualitative. So first of all, we could ask, how long does it take that TT of F minus EF is closed in L1 norm in average? And that's the mixing time. And we can ask for the return time. How long does it take that TT of F of Y minus 1 is less than epsilon? And if you have ever heard of a green function, what we want to have here is that the supremum of the green function in x comma y is less than epsilon for all x, y, and t bigger than t0. So this is the return time. And of course, the return time is larger than the mixing time. Which of one is the decoherence time? I leave that to you. So the main concept of this talk here is actually what is called the modified logarithmic Sobolev constant. And that again has turned out to be a fruitful concept a priori for no reason except that it works. So return time here is defined differently. So we look at the relative entry of TT of F. So this is how after some initial value this has distributed, and we want the relative entropy with respect to the maximum mixed state to decay exponentially in comparison to how it was at the beginning. So if you have a very if you're very close to the equilibrium, then this number here is very small. And then, this will only decay very slowly, but whereas, it's this exponential decay. I think you can look at this in this way. And we work with the complete version if we just replace functions by matrix valued functions. And that turns out to be what we need. And I want to explain to you why this is the thing we actually need. So we use this concepts to all of these different concepts somehow, the lambda or the T epsilon are all measurements of how long does it take until we are close enough to the equilibrium. So there are different ways of measuring this, but that is kind of the point of this analysis. So the classical results is that the mixing time is smaller than the return time. Then there is this constant of the log-Sobolev constant. So I will not explain what log-Sobolev constant means. The reason for that is that, this is 40 years of research and there are already overviews of overviews. So we are talking about hundreds of pages. So I cannot give you a historical outline. It's somehow comparing relative entropy and the energy form, right? So this is called the energy of F with a certain generator. And so LSI implies MLSI. And so this is what I want to mention is that for graphs, something really nice happens, that the return time and the log-Sobolev constant, they are tightly connected. I mean, up to some log, they are the same. So there have been tools in the literature and over the last so many years, which have found ways to actually calculate some of the return times. But I have to also tell you that even if you start with a very simple example, calculating these constants exactly is kind of a nightmare. Because, even for, the best reason is that for heat semigroups or manifolds, although we know that there's a green function, the exact form of the green function is often not known. It's like calculating an eigenvalue, and that's a hard task if you don't have very specific information because the concrete eigenfunctions we don't know. This is a similar kind of issue. You have to use tools to estimate them, but calculating exactly is almost impossible. Good. So now let's do just the quantum jump, right? So we translate everything we learned from the classical case to the matrix case. And now we just have to talk about, okay, what is the generator of a semigroup? Because that's my continuous time evolution, which I want to consider. And this continuous semigroup is just given by a second order differential operator. That's what we learned from the manifold case. The analog of a second order differential operator is given by a double commutator, right? So a commutator AB is AB minus BA. And if we do this twice, we get a double commutator. And if we do this in the form AJ dagger, then this is called the Lindbladian. And what he proved in the 70s is that all generators of completely positive trace preserving semigroups have this form. So it's a complete characterization of the dynamics we should consider on any multi-dit space. So that's good news. These examples with the unitaries, where these matrices here are essentially unitaries, it doesn't look, these two forms do not actually look the same, but they can be transformed from one into the other by some algebraic multiplication, which are easy. But these random unitaries, which we have seen before, and the weights, they actually occur as special examples of this Lindbladian. And that's what we are going to use. And something more, it's also known in the literature by actually Appelbaum and Kümmerer, that if you want to understand the time evolution of such a semigroup, it's given by expected value over these random gates, and exactly the random gates which I mentioned at the very beginning. You look for all jumping times, you write down the unitaries which occur, and then you average over all times which occur up to a certain moment t. So this means that the continuous evolution can be written in terms of these random gates. And this is actually a very quantum thing. And so the point is that for classical quantum groups, these unitaries are not so explicit. They are often contained in the random box. So this is a reformulation. But finding these unitaries is a particular easy for generators on matrix algebras, right? Does the return time mean how long until the states happen to unmix? Yeah, so mixing time and return time both measure how long does it take before the state is almost has weights which are, is totally mixed. I mean, in our scenario. And so return time is stronger because we don't measure as an average, but in maximum, right? I mean, so this state is very, very close to being maximally mixed. I also probably should mention something in this context. I'm working here with the eigenstate being a maximally mixed state. That is physically not the best choice. I mean, there are other states which would be better suited in applications, particularly pure states. But what works nice is with temperature states. So there is some theory which you can go from mixed to some other states, for instance, ground states. But that requires extra work. So this is just, some preliminary work where the eigenstate is the maximum mixed state. Good. So we understand some quantum dynamics. And then there are some good news and bad news. I mean, that you can estimate the mixing time by the log Sobolev constant, 1 over the log Sobolev constant times the number of qubits. That's still true. So if we estimate this quantity, we can actually say something about the mixing time, and everything else which has been done in the commutative case is now translated into the non-commutative case. But there's a big caveat that's more, a mathematical issue. The tool which they usually use is the word hypercontractivity. And then they have a certain inequality, the famous Rothaus inequality, and that works nicely in a ergodic situation and fails in matrix system. So we are also in the situation that the techniques which are classically working for these matrix valued versions completely break down. So this is what we have to accept. So we can use the concepts and we have some hope because they work nice in the classical setting, but not everything goes over without pain. So then we need some help from representation theory. Yeah, I have to explain that. So let me just do this. Yeah, so we start with a nice group. It's my nice group, and we take the unit here, and then we have a certain number of good directions and a certain number of bad directions. Yeah, so these are the bad ones, and these are the good ones. And then we take this group and send it to the unitary group of a Hilbert space. So this is another group. And then again, we can send the unit to the unit, and whenever you have a representation, it will copy these directions. So if we have these vector fields xj on G, they correspond with this analogy u of xt. Xj is e to the it aj. So the xj's, they are corresponding to aj's. So there's a one-to-one relation. So a one-to-one relation between certain Hermander systems on groups, and by a representation theory, they give some Lindbladians on finite dimensional Hilbert spaces. So this is what this is saying here. We have a certain differential operator, delta H, and we have a certain induced Lindbladian, which we call also lambda H, which is given by these differentiation of the vector field directions. And then the help we get from representation theory is that the quantum dynamical system is a subsystem of a matrix valued Sub-Laplacian on a group. So in other words, if you want to understand Lindbladians, you just can find a group, understand the heat analysis on this group, and then go back and deduce all the properties you want from understanding this commutative system, right? A group with certain classical interaction. But in order to do so, you have to do this with matrix valued coefficients, because these matrix coefficients are used in this diagram, which I'm not writing down very explicitly here, right? I mean, in principle, you send an operator to something like pi of t at g is u of g star t u of g. So there is a way to embed your quantum system into a semi-classical system, right? This has some commutative action and some matrix valued set of constant coefficients. And so once we control the group, we control the Lindbladian. And then we control all the times I mentioned: return time, mixing time, complete Sobolev constant. Everything else will be transferred over as long as we can work with matrix valued function. And then it is simply so that these matrix valued functions were ignored in the literature. An example for what happens here is the following. Start with a Lindbladian, like this. Then we can also go back. We can go, this is the second statement. So if you have a given Lindbladian, you can also find a group and some directions backwards. So you can go from group to Lindbladian and from Lindbladian to group. If you do that, and then work with other representations than the standard representation, we come to what is called the collective Lindbladians. And since they're a little bit mysterious, let me write them down for two, right? So you have your generators AJ, and now your new generators are AJ tensor 1, 1 tensor AJ. Or you have 3, then you take 3. And that is very much parallel to W states, right? You change one thing or you can perform the other component. So the construction is rather natural. And then what we can show is that if you control all collective Lindbladians, then we actually have to control the group differential operator and vice versa. So that's the philosophy. If you control all collective ones, then we have to essentially understand the commutative system with matrix valued coefficient. Good, so that gives us an idea. But we do have a result on scrambling. Here it is. So if we control the complete mixing time for the generator, right? So our generator here is summation Wj, Uj, yeah, so this is our generator. So if we understand the mixing time for this L, but also for this L2, right, the collective Lindbladian. So we have to understand the complete mixing time for L and the collective Lindbladian, then we control scrambling. And the mixing time and then the time is something like logarithmic of the dimension of the underlying Hilbert space over this lambda CLSI of lambda 2. So essentially, we get exactly what you expect. So if I write logarithm of dimension, that's the number of bits, right? So the time is proportional to the number of bits, but it depends on the mixing quality of our generator. And not only of our generator, but our extended generator or collective generator. So that's a theoretical result, but it does give you some examples where we can actually say something about scrambling. And just for those who actually have been listening to some of my courses, this uses Renyi entropies and some inequalities, exactly the type of inequalities which I proved in my class this spring. So it's just it's not unconnected to the work, and it also uses some tool from the mathematical theory I come from, and there's some operator space things. And if you haven't never heard about these things, that's okay. But this is how I moved into this field, right? I discovered these inequalities, and there's a connection. Anyway, so we have some time estimates. They also depend on, we have to assume that the amount of radiation is sort of proportional to the amount of non-radiation. And if this kappa here, this all here depends on kappa in an implicit way, because you have to keep something and you have to throw something away. You cannot keep everything. If not, this cannot work. So all of this is, technical, because it depends on all the input data we have, but eventually it works. It is also somehow, it uses techniques which have been in the literature before. So it's not all novel, it's just adapting some of this to this context. And I think the relative entropy estimates have been a little bit overlooked in this context. Good. So I talked about the complete log Sobolev inequalities, which is exactly this decay estimate for the relative entropy. I think I defined this before, and since we are getting towards the end of the talk, let me just mention the open problems. We believe that every ergodic sub-Laplacian on a compact manifold should have some estimate for the CLSI constant. Just doesn't mean we can prove it, but that would be the most far-reaching conjecture I can imagine. And it would somehow say that every diffusion process has to mix eventually, has to go back to equilibrium relatively in a certain amount of time. The next conjecture is that this is true for all collective Lindbladians of a given Lindbladian, and then a weaker conjecture is that for every finite dimensional Lindbladian, we can estimate this constant from below. It's not zero, right? So there always is a decay time for the relative entropy. That are our, these are the open problems we try to prove, and in some cases we know the answers, in some cases we don't know the answer. But that's kind of what we're doing. Yeah, here somebody asked what's about the absolute value of C. This is just a dimension of the corresponding, if you have this split, the Hilbert space is CD, or formally a tensor product. This is really a tensor product split, and we have to understand the dimension of these splits. So we always have to absorb a proportion of a gamma radiation, which is proportional to the size of the whole black hole. And that's, of course, waiting for a little bit, right? I mean, that's a non-trivial time to wait before we can we decipher Alice's secret. Yeah, so there are some known results where this works. So we can use curvature, and when we have some bounds, the folklore results are about fermionic and bosonic systems. They have been known for a long time in different versions. I think these problems have been solved before they were posted. So these things have, the techniques to solve them are known for a long time. There are some generators which are nice, which are of the form identity minus E, and that is the closest thing to decoherence. If you take for E the decoherence matrix, which sends everything to a diagonal, then this has to do with decoherence time, and that has been studied very extensively by Data and her co-authors. Another great example are graph Laplacians. I mean, eventually we want to prove some mixing time estimates for graph Laplacians for the ground state of a graph state. We are not there yet, but we at least understand the semigroups, and the semigroups are really, if you have a graph, then for every point you have some nearest neighbor interaction, and what you do is you somehow average every point around its neighborhood, and that is the graph Laplacian. And then so we take f of y minus f of x, and we average that over all neighbors. Yeah, so that's the graph Laplacian. For those objects, we do have results. The graph Laplacian is actually a nice result, because what we do here is, this idea goes back to Nick. So we first prove it for the interval 0, 1 with some kind of continuous generator. Then we prove it for a line, right? We take a graph which is just given by a line, maybe even cyclically connected. And then the last piece is, if you have an arbitrary graph, we use a spanning tree. And then reduce the spanning tree. We use the line to prove something about the spanning tree, and the spanning tree has fewer edges than our original graph Laplacian, and fewer edges means it mixes slower. So the way to prove this is often kind of rather indirect. We have some kind of good examples which we can work with, and then we have to gradually reduce it to these small number of examples. That's how this works in this particular context. Yeah, so examples for scrambling. Yeah, I have two nice examples. So let me say something about the first example. So the first example is, we first start with M2, or just the X and Y matrix. And since SU2 is more or less S3, this scrambles. Okay, so here we're using a group, which helps us to understand something. And then if we understand the group, we understand all the Sub-Laplacians, and everything is fine. So here we go from group to Lindbladian, and then we win. Now, if you do this so this is for 1 bit, right? So, but if we do this for M2 tensor D, so we are working on a D bit space. then we can just use X tensor 1, 1, 1, 1, 1. So we use a Pauli matrix in every register. Y tensor 1, 1, 1. Then 1 tensor X tensor 1, 1, 1. 1 tensor Y tensor 1, 1, 1. And so on. So then we can use some kind of, yeah, in principle, I mean, so here the mixing time is essentially like D, right? So this is how long we have to wait. And we do this by some kind of inductive procedure, right? So you know, if you understand it for the 2 particles for 1 bit, then you can use, so this is a technique, it's called the martingale method. So this method allows you to actually deduce the result from this case to multi-dits. So this means that, yeah, you're just waiting essentially the same amount of time, and you just have to use more generators, but you're also normalizing to much larger states. And you know, the dimension, so this is kind of yeah, so it scales in the order of the number of bits, and I think that is a, you know, for large scaling properties, that is an acceptable scaling property. It's actually probably the best I can think of ever, right? So this is similar results have been proven with a slightly different model of randomness, but so this is kind of the best possible result. So these iterative Pauli matrices in different registers, that is where you should expect this I3 scrambling to happen. So that is the content of the first example. The second example is about quantum Fourier transform, and that is much harder. And I think the most important case is that, you know, even there's just really a lot of work for understanding concrete situations of concrete unitaries and what is the right time. There is not a sledgehammer method to do this at the way. There are some tools, but somehow in every situation you have to adapt them reasonably well so that they actually work. And if you want to have a precise estimate on the time, there are also some technical components to do the calculations. So that is where we are at this moment, but there are many interesting examples from finite groups, which we would like to understand much better. And we're at the moment, we, you know, every time this is a hard task, even if we have the theory available. Okay, guys, that's it. Thanks for listening.
Thanks, Marius, for a very interesting talk. Do folks have questions? Please feel free to chime in or post on the chat.
Hey, Marius, question for you. Can you further comment on the measure I3? Because its information theoretic meaning is not so clear, and I'm wondering if you were to use some other measure of 3-party correlations, how this would change. Oh,
okay. So let me write down. So the I3 is very funny. It is really, in our context, we should have a 4-partite state. Okay, so I3 is, they tell you it's about 3 parties, but it's wrong, it's about 4. Mm-hmm. And we always should, coming back to Paul's question, we always should have a pure state here, right? So, yeah, I mean, if you apply a unitary on part of the state, then it remains pure. So we really have to estimate this for pure states. And then the information ADB here is H of A plus H of D plus H of B minus H of AB minus H of AD minus H of DB plus H of ADB. Okay? Mm-hmm. So, and it is the same as I3 of a CB. So it's, you know, it's a highly symmetric expression. So this is symmetric under the permutation group in 4 parties essentially. And it's like inclusion-exclusion principle, right? 1 particle goes in, 2 particles go out, 3 particles go in. So it has this mathematical symmetry structure, which is amazing, right? So the I3 thingy is interesting in the context of holographic states coming from black holes, right? And there it's conjectured to be negative. I3 in principle could be positive and negative and whatsoever, right? But this is all, you know, it's an really intriguing concept. You know, what is a higher, I mean, the background for this is what is entanglement in more than 3 parties, right? You know, nobody, we all try, but, you know, nobody can claim they do know. This is an attempt to quantify that. Yeah, it's an attempt,
Okay.
but for our purpose, it is actually much simpler to understand. So what do we prove? In our progress, we prove that I of A D is very small, and I of AC is reasonably small. And that is scrambling. Or at least it implies scrambling. Mm-hmm. Okay? So in terms of the black hole, this is really, really, really easy to understand. I mean, you know, we have A, C, D, B. So for this, you know, this is if you want a lemma, right? So this means we only have to understand this 3-party system, A, C, D. Yeah? And we went in here with A prime, B prime, and here we applied this mixing unitary, which scrambles everything around. I mean, which really destroys all information. So we have destroyed the information between these two and these two by proving that the mutual information is small. So both of them are small or not too big. And that is, so that is an information theoretical explanation for what happens. And that I can somehow live with, right? Because, you know, mutual information from A to C, well, from A to D is pretty clear. You have a little bit of gamma radiation. The secret is to the left. There's not much, you know, they're almost independent, right? So that makes sense. Same from A to C. C is a little bit bigger, but this is why C cannot be everything. Because then we would be able to understand the secret. No. But if they are both small, and the funny thing is that, you know, one of them small and one of them reasonably small is a very funny side remark in the paper by Haojian and Preskill, but it's really the key. And they often, you know, allow 1 bit there. But it's really a matter of the setup of the problem. Yeah. Okay. And it is also vastly helped by the fact that I assume that this state C, B prime B, that if you look at row B, that this is maximally mixed. So since this is maximally mixed, this helps. And that's how they, you know, get it all together. But, you know, you have to use this, and then it's just, you know, mutual information being small between A to C and A to D. I think that's something we can accept and understand. But this is under the helping assumption of this state which Bob puts in a very special form. And that is why it actually works, right? So that's the trick, right? So the I3 is fancy, but it's not really necessary to understand what's going on in this particular situation. So yeah.
Okay. Thanks.
And it looks like Paul posted a question on chat.
So it's known that making repeated measurements can inhibit state evolution. I cannot fully answer that question. So the point here is that we are doing this random. So the question is whether the I3 approach avoids state evolution. No, that's not the right way to think about it. So the point is the following. Let's go back to this picture here, right? So we do have some state evolution along this unitary, even if this is a product of these guys, right? I mean, we are approximating this by a product. But since we are taking the partial trace, we are just looking at the D component and we forget the C. That somehow allows us, this is what prohibits state evolution. So this is what produces the mixing. And then the state evolution, because because the C and D are random, you cannot find the correct eigenstates of the unitary evolution. I mean, so the eigenstates of the unitary evolution, they are kind of so orthogonal to the decomposition in C and D that we don't see it, right? That's sort of how I understand this. I mean, we don't need, no, I mean, yeah, the rest of the question I cannot answer, Paul. Unfortunately, I'm not really sure what to say. So because we're doing unitary operations and a partial trace, we are in a pretty general, in a general channel situation, right? I mean, if you think about Paul's talk, Eric's talk, right? I mean, unitary evolution plus partial trace, that's as general as it gets for a channel. Yeah. Other questions?
I had one simple question, Marius. So for the case of Laplacians, which came up at the end, if we just have let's say we have a simple undirected unweighted graph, is the LSTI constant small when that graph has a small cut? Is that a correct intuition or not really?
I mean, so this is hard. I mean, we all expect that I mean, there's this, the log Sobolev constant is, I think, related to these expander properties.
Mm-hmm. Yeah.
But for the concept we need, these complete log Sobolev inequalities, this connection is completely not understood. We don't have, I mean, many of the classical tools don't work anymore. And so, I mean, of course, I mean, the CLSI constant is sort of a substitute for the eigen, this second largest eigenvalue, right? Yeah, but it's sort of harder to estimate than the eigenvalue, much harder. And in some cases, these things are proportional. In some cases, they are not. So I think this idea of producing some direct applications of expander techniques in this context would be great, but we are not there. And it could be that this better works not on the first level, but I have the feeling it could work on the second level. You know, I talked that we have to control these second order Laplacians L2s, which for the scrambling property. And I think it's closer related to that second order monster than the first order. So that's a vague intuition, but that's all I can say. But the direct connection is completely open. And in fact, it would be really nice to find some more other direct proofs to prove, to control these log Sobolev inequalities, right? And I'm also not so sure whether relative entropy has been studied even for graphs in the way it should be in this context. Yeah. But it has to do with these Talagrand type concentration inequalities, and they're related to the max cuts. Yeah. And that's the, I mean, there is a relation, yeah, which is rather, so these LSI constants, the modified log Sobolev, they imply the Talagrand type inequality, concentration of measure. So they're stronger. But the other way is open, how to get them.
Okay, thanks. Any other questions? Okay, thanks again, Marius. I guess we can stop there.